You probably feel like Le Chatelier's principle has been stalking you all semester. And you are right, it does. We're going to use Le Chatelier's principle to predict the dependence of cell potential on changes in concentration of the solutions that we're using in a galvanic cell. It's going to be awesome. So here's a simple redox reaction that they've got set up here with magnesium and lead. They have the cell potential as 2.24 volts. And we assume that's under standard conditions. That little degree symbol by E cell means standard conditions, which one of those conditions is that the solutions are 1 molar. I'll make note of that. Standard would be 1 molar solutions. The other one is like 25 degrees Celsius. Okay, so let's say I change the concentrations. We can use Le Chatelier's principle to predict the effect on the cell potential, the force pulling the electrons through the system. So we're keeping the lead at 1 molar, but what if I increase the concentration of the magnesium ion? If I increase the magnesium ion, that's on the product side, this thing would shift in reverse. If you increase the concentration of a product, we shift away from what you're adding, reverse. If we're shifting in reverse, we would say that this cell potential will decrease. We're not going to pull as many electrons through the system if we're shifting in reverse. So you should see the cell potential something less than 2.24 volts. Something like B. Now what if I take that magnesium concentration and decrease it? So the lead is staying standard, 1 molar, and we decrease the concentration of the magnesium. Remember, if you decrease a particle in the reaction, we shift to produce more. So now we'd want to increase the concentration of the magnesium, which means we're going to shift it forward. If we shift more forward, the cell potential should increase. Super easy, right? Now there is an equation. I don't know if you've ever heard of this Nernst equation. It's in the book if you are fascinated by reading the chapter. The Nernst equation can be used to calculate the exact change in the cell potential. You do not need to do that anymore. So if by chance you are reading through one of those AP study guides, I bet in the electro section they might have something called the Nernst equation. It's actually very cool and very fun, but you do not need to calculate the change in cell potential anymore. Now it's just all qualitative. We would want to be able to predict if it'll increase or decrease, but you don't need to know the exact change. Check out C. This one's kind of interesting too. What if a solution of sodium chloride is added to the solution at the cathode? Okay, so I have to think of a few things here. Number one, the cathode. Red cat. Okay, so I want the reduction equation, and reduction involves gaining electrons. So if I kind of think about the two half reactions here, I'm referring to the half reaction that involves gaining the electrons. That should be the lead, right? The lead plus 2 would gain 2 electrons and form the solid lead. So here's the half reaction that I'm referring to. What if I add a solution of sodium chloride to this half reaction with the lead? Most chlorides are aqueous. All sodium compounds are aqueous. Most chlorides are aqueous. There are 3 chlorides that do not dissolve: silver, lead, and mercury. So lead chloride is a very common precipitate. So if I were to add that chlorine ion, we're going to form a precipitate of lead chloride. Remember we kind of said when you precipitate an ion, you remove it from the solution. So this lead concentration will decrease. Okay, so if I look at my overall equation up on top, if I decrease this lead ion, I would want to shift in a direction that replaces more. So to replace that lead, we're going to shift it in reverse. If we shift this thing in reverse, the cell potential will decrease. So anytime we're shifting forward, the cell potential increases. The force pulling the electrons through the system will increase. Anytime we shift in reverse, the cell potential decreases. There you have it. And I think that's the last time, Sally, that might be the last time that Le Chatelier will come back into your life. Until you start studying for the AP test, I guess.